We've said before that one of the most important things we do in math is to build equations that model word problems, and that's what we're going to do in this section. Now, the building of those equations can come to us from a number of different sources. Sometimes the equation is simply a formula that's related to the nature of the problem we're dealing with. If we're talking about the perimeter of a rectangle, for example, it's kind of a built-in formula. A more intriguing kind of equation, though, is one where we have to build on some kind of general idea or some kind of general model. That's what we're going to do in this section. But we've seen this kind of idea before. We saw it when we were talking about direct and inverse variation. For direct variation, you may recall that if y varies directly with x, then it implies the existence of a constant that we could call k, such that y is equal to k times x. So we have that fundamental general idea for building a model for a solution. Then we have some kind of experiment that it allows us to identify the value of k, and away we go with being able to have an equation where we can answer questions about the y and the x involved. Okay, similar idea here. Now, there are a number of different models that are in the family of exponential or logarithmic, and they are illustrated in your textbook, and I suggest that you have a look at them. Let's kind of examine the algebraic form of them here. We have a couple of exponential models. One is for growth and the other for decay. The growth model is often used to emulate population changes. The decay model is often used with radioactive material and carbon dating and such things as that. Now, just notice the nature of the equation. It says y equals ae to the bx power. Now, the bx, notice the variable in the exponent here, hence an exponential equation. And we know that the nature of exponential equations is that we have a continuous curve that it is continually either rising or falling. Well, for the growth model, it will continually be rising, and it is for that reason that we're requiring here that the b value be positive. For the decay model, the b value turns out to be negative. You see, if b is positive, then negative b would be negative, and this would be a declining graph. Okay, the idea with the a and the b now are constants, and the x is a variable and the y is a variable. Now, a is generally, when we talk about population, this is initial population, and the y would be a resulting population, presumably after some period of time. And x is going to be the role of time. So it's time in terms of population when we get to that kind of model. Okay, so that's the idea with these equations. Another kind of model is a Gaussian model, and it has this kind of equation. Looks a little convoluted here. All the action is out here in the exponent. But this kind of model is one that has a graph which is kind of a bell-shaped curve, and it's used often in statistics. This one is a logistics growth model. And look at the form of this. It just has a different kind of look than the others and a different kind of feeling. And once again, we would end up experimenting and plugging in information and developing this for a particular kind of situation. This one, by the way, has a graph that kind of starts out slowly like this. It's slowly rising, and then it ramps up really quickly, and then it kind of levels off at the top. And this is the kind of model that is useful in emulating the growth of bacteria or viruses or something like that, because the ramping up is when the food supply is plentiful and so forth, and those rascals tend to multiply really quick, and then it kind of levels off when the food supply goes away or there is some constraint in the amount of space that they have in which to grow. So that's the logistics growth model. The logarithmic models now take this form, and there are other forms that we could write these in, but we'll be studying the logarithmic models in these forms. It's a plus b ln x or a plus b log x, and these kinds of models are used in emulating or illustrating or showing the magnitude of, or excuse me, I should say the intensity of earthquakes, using a Richter scale. The Richter model, you see, the Richter scale is a logarithmic kind of scale. Well, let's jump back to the exponential models and consider a problem. Here's how we build on this general idea. Here's the model that we're building on, and let's say that in a city in 1990 the population of the city was 2 million, and in the year 2000, 3 million. We'd like to know the approximate population in the year 2010. Now, to start the process, we think about our model this way. Now, A is the starting population, Y is going to be the ending population, and X is going to be time. All right, and then B is going to be some constant that tells us about how fast we're growing graphically. It's easy to see graphically, the kind of shape of that graphical curve. And so we need to find the value of B early on in this situation. And we find that by performing some kind of experiment or by using the given information. All right, here's how we would use the given information. Now, you know that these numbers can correspond to ordered pairs. And we have to start with when we have time-related problems, we start with a time basis. And the basis here is 1990. So we would let 0 stand for this time. And at that point in time, the population is 2 million. And for the year 2000, since it's 10 years from 1990, 10 years have elapsed here. So 10 corresponds with the number 3. So we have a couple of ordered pairs. But here's how we can jump right into the model. For the year, in the year 2000, you see, we have the start population and the end population. For the year 2000, here's how the model works. The starting population was in 1990, and it was 2 million people. The ending population was in the year 2000, and it was 3 million people. All right. Now, the time is 10 years for this period of time. That is from 1990 to the year 2000. Now, with this, we're going in and we're trying to solve this for B. We're trying to get at that sort of, when we were talking about this in variation, we were looking for the constant of proportionality. And here, this is kind of a constant of exponentiality, you see, is what we're looking for here. And we're using the information from our experiment or the information that's given here from a historical standpoint. All right, we just need to solve this equation. I'm dividing on both sides by 2 to isolate e to this exponent. Now I need to jump into the exponential world by applying natural log on both sides. Now we have the natural log of 1.5 is equal to 10b. Dividing on both sides by 10, I find this fraction to be equal to b. Now we could at this point approximate this fraction, but we're going to use this back in our model. And if we're going to use this, then it's valuable for us not to approximate. Because if you use an approximation and then operate on it, perform operations on it, it turns out that you can multiply the error because an approximation contains an error, however small. So let's use the exact value here for b. So we would come up here, we would take our model, and now that we know the value of b, we would put it in. Now notice I'm using t as the variable here instead of x, because that's the nature of this particular problem. Now, with this, we can answer any number of questions involving time or population. We can say, okay, I'd like to know the time when the population will reach, say, 5 million, or something like that. And so I could put in 5 here and solve for t. Or I can take a period of time and put in here and solve for y, that is the population after a certain period of time. Now, the nature of our problem is that we're looking for the population in the year 2010. So let's see, what would t become? Well, we started as the basis year, 1990, and so you calculate a period of time from 1990. So from 1990 to 2010 is 20 years. So we use 20 for t, and away we go. You see, and just this is just a calculator push at this point. It looks a little complicated, but it's not really a big deal. We find that y then is approximately 4.5 million, and that means that the population of this city is predicted to be approximately 4.5 million people in the year 2010. Let's look at a problem involving exponential decay. This problem involves a substance which has a half-life. Substances having half-lives are substances that dissipate over time, and half of the substance dissipates over the half-life period. That is, in this problem we're talking about a substance that's radioactive iodine, one of the byproducts of making nuclear energy. And the half-life period is only 60 days. Well, that just means that half of whatever we start with is still around after 60 days. And after another 60-day period, half of that amount is around, and so on. Now, some radioactive materials, some of these byproducts of nuclear reactions, stay around for thousands of years. And one of the great controversy has to do with how do we keep that material, and we have made it, and it's deadly, and where do we keep it, and how do we keep it, and all that kind of thing. It's one of the great fears of using nuclear energy. Anyway, other substances having half-lives are not so intrusive. One such substance is an isotope of carbon. Now, all living organisms are carbon-based, and a lot of times the age of organisms can be dated by using this carbon-14, this isotope of carbon, because it has a particularly stable half-life, and it has a very long half-life, so it can be measured, and then the age of substances that have died, the bones, for example, of dinosaurs and things like that, can be established quite easily or very accurately using that method. Okay, and here is that method. Here's what could be used in that circumstance, but here we're only using radioactive iodine. At any rate, let's suppose that 20 grams are released. 20 grams of this substance is released from this nuclear reaction. How long will it take for the radioactive iodine to decay to a level of 1 gram? Well, we could figure it out by saying, gee, in 60 days, if we start with 20 grams, in 60 days we'll have 10 grams. In another 60 days we'll have 5 grams. In another 60 days we'll have half of that, and so on. So we could kind of get at it like that. But let's make a mathematical model to tell us how long it's going to take for 1 gram to remain. And we start with our basic model, y equals ae to the bt power. Now notice I'm using t as the variable because we're talking about a time here. We could talk about this as an x if we want to. Also, I might mention to you that sometimes instead of using an a here, a c is used here for the initial quantity. And sometimes this constant that is going to tell us about how the graph behaves is a k rather than a b, but it doesn't really make too much difference. All right, it's important to know that the a, this coefficient of e, is an initial quantity, and the y is the quantity remaining after a certain period of time. That's a very important idea. Now, the first thing that we generally do in problems like this, where we're using kind of information or an experiment, is to establish the value of that b, or in some cases k. But so we're using the information, and here's how we use it. We have a half-life situation involving 60 days for a half-life of the material. Now, in this problem, we are starting with 20 grams of the stuff, and after 60 days we have 10. So we could kind of fill in like this if we want to. You see, and now dividing on both sides by 20, we get this, and then 1/2 equals e to the 60b, and now we would go about solving for b. But I think it's important for us to realize that there's nothing magical about using 20 and 10, because after all, if we start with any quantity right here, we're going to have half of that amount over here. That is, we could start with 10 and have 5 over here. We could start with 4 and have 2 over here. And in all of those circumstances, once we divide by this coefficient, we're going to get 1/2 over here. As a matter of fact, we could start with a very general value a, you see, and then over here we would say, okay, 1/2 of a is remaining after 60 days. You see, and then a divides out on both sides, so we have the 1/2 over here as expected. All right, now let's continue from here. We would go into the exponential world by using logarithms. We would say ln 1/2, well, I'll use 0.5, equals ln e to the 60b. We're solving for b now. ln 0.5 then is 60b times ln e, which goes out. Dividing on both sides by 60, we find b to be ln 0.5 over 60. Now, it's important to realize that ln 0.5 is a negative value, and of course 60 is positive. But because we have a fraction that turns out to be negative, the model, the graph of the model, will descend. You see, that's why this is a decay model, because we're constantly reducing the amount of material that we have over time. All right, now let's use this information about B to solve our problem. We rewrite our original equation. Now 20 is the initial quantity of material, and the B value has been established, and that allows us then to solve any number of questions or answer any number of questions having to do with time and quantity remaining. You see, we could make this quantity remaining anything we want to and figure the time, or we could say how much quantity is remaining after a certain amount of time. We could fill in for either one of these and solve for the other. Okay, in this problem we want to know the time associated with a quantity of 1. And so we just pop in a 1 here and then solve for t. So let's see, we would divide on both sides by 20 to clear this coefficient, so we would have this, and then we would jump into this exponential world by using logarithms, ln on both sides, and then on the right side this exponent becomes the coefficient and the ln goes out. And now we'd like to isolate the t. One way to do it is in 2 steps. We could use a 1-step method, but the 2-step method is to clear the fraction first, multiply on both sides by 60, and the fraction clears here, and we have 60 as a coefficient over on the left. And then we would divide by ln 0.5 on both sides, and then evaluating using the calculator, we would find the time to be approximately 259.3 days to have 1 gram of that material left. In this problem, an exponential equation is used to model a population problem. It says the population P of a city is given by the equation P is equal to 25,000 e to the kt power, where t is the time in years with t equals 0 corresponding to the year 1990. Now, let's stop right there for just a moment. The situation is implying that in 1990 the population of the city is 25,000. And since that is the basis upon which we're building our equation, t, the time, is 0 corresponding to that year. All right, let's continue. In 1945, the population was 3,350. Find the value of k and use this result to predict the population in the year 2010. Now, we're asked first to find the value of k. We'll use the information about the population size in the year 1945 in order to do that. So we'll replace within our equation 3,350 for p. And in place of t, we'll write the time of negative 45, because 1945 is 45 years prior to 1990, the basis for our model. All right, now let's solve for k. Dividing on both sides by 25,000 gives us this result. Notice we cleared the 25,000 on the right, we get a decimal on the left. Now we're in a situation where we apply natural log on both sides, giving us this, and on the right we apply the power property to write negative 45k as the coefficient of ln e. Of course, ln e is 1 and it goes out. And now, dividing by negative 45 on both sides, we find k to be this rather long decimal. So what we'll do is replace this value of k into our mathematical model. So k is replaced with the long decimal, and we have this relationship between population and time. Now notice, with this relationship, we can find the population given any amount of time after the year 1990. Or on the other hand, we could find the amount of time that it takes for the population to reach a certain level above 25,000. In our problem, we're asked to find the population in the year 2010. So what we'll do is we'll replace t with the amount of time that has elapsed between the year 1990, our basis year, and the year 2010. Well, that's 20 years. So let's replace t with 20. Now it's a calculator problem, and we simply multiply 20 times the long decimal, raise e to that power, multiply by 25,000. We find p to be approximately 61,079. So we can write our answer. The population of the city in the year 2010 will be approximately 61,079. Here is a somewhat different kind of population problem. A conservation group releases 100 animals of an endangered species into a game preserve. The organization believes that the preserve has a carrying capacity of 1,000 animals, and that the growth of the herd will be modeled by the logistics curve
given by this equation where t is greater than or equal to 0 and where t is measured in years. If the herd size is 134 after 2 years, find the population after 5 years. Our first task is to find the value of k. Now, to do that, we replace within our model information about the herd size of 134 after 2 years. That is, we'll replace p with 134 and we'll replace t with 2. Well, once we've done that, we notice first of all that the exponent on e in our denominator, the negative k times 2, would probably be written as negative 2k. Now, to clear the fraction on the right side, we'll multiply on both sides by that denominator, giving us on the left this product. On the right, of course, the fraction clears. One way to proceed from here would be to divide on both sides by 134. Dividing on the left by 134 would leave the binomial. Dividing on the right would give us this decimal. Now, if we subtract 1 on both sides of the equation, the 1 will disappear on the left and the number on the right will be reduced by 1. At this point, we'll divide on both sides by 9 to find e to the negative 2k to be equal to this decimal. At this point, we are ready to apply natural log on both sides of our equation. Now, in doing so, on the left, the negative 2k will become the coefficient of ln, and of course ln will go out. Dividing on both sides by negative 2, we find k to be approximately 0.1656. This information is replaced within our mathematical model, and the model looks like this. Now it's time for us to go back and complete our problem. In our problem, we were asked to find the population of the herd after 5 years. So we'll replace t with 5. Now let's go through the calculator sequence here. In the denominator, multiplying 5 times the decimal, and then raising e to that power. Then 9 times this long decimal, adding 1. And then finding the quotient, we discover that p is approximately 203. So the population of the herd after 5 years will be approximately 203 animals.
This next situation involves a logarithmic model. And the most notable use of logarithmic models, I think, is probably in the measurement of the magnitude of earthquakes. You know, a Richter number, a Richter scale is used to determine that magnitude. And a Richter number is actually a logarithmic type of number. That is, the Richter number is simply the logarithm of the intensity of an earthquake. Now, and actually it's the intensity over the initial intensity, which is 1, but it boils down to this. Now, the logarithm is common logarithm of the base is 10. So now, why is this Richter number used? Why isn't I simply used? Is the question that sometimes emerges here. And it's because I, the intensity, is measured in very, very tiny units. The instruments that measure the intensity of earthquakes are very, very sensitive. So there would be a lot of units used in measuring the intensity of an earthquake. And so if you were just looking at two very, very large numbers, in comparing earthquakes, you don't want to look at a number in the millions compared to another number in the millions to compare earthquakes, you see. So we put them into the logarithmic world, and then it's a number that we have some reference to. But it's important to realize that these are logarithmic types of numbers. And this is what, I think this is what we want to do in this problem, is to realize the difference in Richter numbers because they are logarithmic in nature. All right, consider this problem. In San Francisco in 1906, there was an earthquake that measured a Richter number of 8.6. In 1989, there was another earthquake that measured 7.7. Now, the one in 1989, you may or may not recall, but it was a really powerful earthquake, and yet this one was 8.6. So 7.7 to 8.6. It seems like, well, gee, if this is just 8.6, that's 7.7. They're not too far apart. These earthquakes were probably just about the same size. Well, that's not really true. And let's evaluate the situation. by doing this. In 1906, if the Richter number is 8.6 and R is calculated as the log of I, let's find the intensity of this earthquake in 1906. Okay, to do that, we'll go from our model here and replace R with the 8.6 and go into the exponential equation. 10 to the 8.6 is equal to I, base exponent, you see. So I, the intensity of that earthquake, is 10 to the 8.6. A big number. All right, and we can put it on the calculator and see all of the digits and all that kind of thing, but I don't think it's necessary here. We know this to be a really large number. In 1989, an R of 7.7, same idea. We just replace R with 7.7, and now we go into the exponential form. 10 to the 7.7 equals I. Well, maybe we still don't have a good reference for the difference in these intensities. So let's make a ratio out of them. Let's consider the ratio of the intensity for the 1906 earthquake over the intensity of the 1989 earthquake. Now, the intensity for the 1906 was 10 to the 8.6. For the intensity in 1989, it was 10 to the 7.7. Now, this is 10 then to the 8.6 minus 7.7, or 10 to the 0.9 power. And this number is 7.94. 7.94. So that just means that the earthquake in 1906 was almost 8 times as intense as the one in 1989. A really powerful earthquake. Well, we're talking about mathematical models here, and we're talking about ways to generate those models. And we've talked about exponential forms and logarithmic forms and variations on those themes, the Gaussian model and so forth. Well, another way to generate a model generally is to take information that is in ordered pair form. So we have a group of ordered pairs, and this information might be historical in nature or something like that. But we can take this group of ordered pairs and we can make a scatter plot out of those ordered pairs. That's just plotting those points. And then after plotting the points, we can use the graphing calculator to draw a graph that best fits those points. So the first order of business is to gather the information. The next order of business is to make a scatter plot. The next order of business is to use the calculator to identify some kind of a regression model. Now, the process is called regression, and there are various regression equations built into the calculator. And some of them will give a relatively better or worse fit than another. And there is a number that gives us information about how good the fit is. And with the calculator, we can see how good the fit is by graphing the scatter plot and then graphing the regression equation that we are talking about and see if it fits. But we have a correlation coefficient that also gives information about how good the fit is. Well, I've chosen some ordered pairs, some information, just to put into the calculator in order to investigate this idea. Let's have a look at the graphing calculator now. To enter the data, we press Stat and then Enter. Now, notice the little 1 is highlighted there for edit, so pressing Enter, and you'll notice that I've already entered the information. Let me show you how each item is entered. If I want to take this 0.9 and change it to 1.6, and I would enter 1.6. Now notice that the digit and the digits and the decimal are being shown at the bottom of the screen. And then when I press enter, they show up in the list. All right, so I'll change it back to 0.9 the same way I did before. I'll just highlight that top item and press 0.9 and then enter, and there we go. And the icon jumps automatically to the next item, so we can enter them in order like this. Well, let's go back to the main screen. I'll press second and then quit. Now we'd like to see a scatter plot, and the scatter plot is accessed by second function and then stat plot, which is the button here at y equals. It's the second function on y equals. Now I'd like to just turn the plot on. The icon is on number 1 now, and if I press enter, then I'm on an on-off switch right here, and it's flashing on, so I'll press enter again. And now I've just turned this thing on. Now the type of plot that I want is the default plot. I'll cursor down, and this is a scatter plot, and these are other kinds of plots that are possible. And I'll go through all of them like this. And then the next thing on the list is that the X list, the items composed of X values, are in L1, and certainly they are because that's the way we entered them, and the Y values are in L2, and that's the way we entered those. So just the default settings are all that we want at this point. We could make different settings, though. We could designate that L3, for example, would be the Y components of these if we had items in list number 3. Also, the marks that are made on the graph can be changed using these various designations. But let's just use the default item, and away we go. Let's go to zoom now. Incidentally, if we don't go zoom and just go graph, then the graph looks like this, and there's our stat plot. Now, we'd like to sort of frame this in our viewing window, and to do that easily, we press zoom, and we want number 9. I'll show you what number 9 looks like on this window. It's zoom stat. I could have either pressed 9 or cursored down here and pressed enter, but when I do so, our stat plot items are all on board. Now we can trace from one to the next of these. I'm pressing trace, and then as I cursor to the right, I see the XY components of each of these items on the plot. And when I cursor to the right, I'm wondering why this one, for example, appears to be black. You see, it's all black, and the others appear to have some vacancy in the middle. Well, it's because, well, let's see, I'm at the second item now. It's 1.3, 2.4, and then when I go to the right one more, it's 1.3, 2.2. Oh, there are two of them that are sort of on top of one another here. You see, and I can cursor over to the right and access all of them in turn. Well, let's see, what we'd like to do now is lay a graph over this, perform a regression, and see what regression fits this information best. And to do that, we'll press stat and enter the stat menu, and now we'd like to make a calculation. So we go to the right, 1 for calculations, and now there are any number of regressions that are possible. Here's a linear regression, a quadratic regression, a cubic regression, a quartic regression, another linear regression. Now this linear regression is in the form a plus bx, and we noticed that earlier on the board that I mentioned that idea, and this one is in the form ax plus b. Here's an ln regression, which is a natural logarithmic regression, and an exponential regression. We also have available a power regression and a logistics kind of curve regression. But oh, and here's another one, a sign regression, which we may get to at another time in this text. But let's go back up and let's perform a linear regression. Let's do this first linear regression. When we press enter, then we go back to a main screen, and then when we press enter again, the regression calculations are made within the computer. Now notice that it's saying that in this model, in this mathematical model, the value of A is this, the value of B is this. And these two numbers are correlation coefficients. Now the correlations are not particularly high, particularly R squared is not particularly high. We would like for this number to be 0.999 or something in that neighborhood to match the information well, or to match the data that we have on board for the stat plot. Well, let's see what the graph looks like. To do that, we can press y equals, and to enter the equation, this is what I think is so neat. We want variables, VARS, press that button, and then we'd like item number 5 for statistics. It's this item, and I can cursor down to it, as you know, and press enter, or I can just press number 5, but it's statistics, and I want a statistics equation, so I'll cursor to the right twice for equations, and the very top one is a regression equation, and so I'll press enter, and it automatically enters that equation for me according to the regression that we just performed. And now I can see the graph, and you see that that linear equation doesn't match the data very well. It kind of goes through the middle, but we'd like for the graph to come close to those points if that's possible. Well, let's perform another regression. Stat, and then to the right, and then down. And let's do let's say an exponential. No, let's save the exponential for later. Let's do the natural logarithmic regression. Now, you know a natural log curve is a curve that's basically like this, and yet our data that we see is more like this. It's more of an exponential kind of set of data. So let's just see how the calculator is going to do a natural logarithmic regression on this and what the graph looks like. So I'll press enter here and then enter again, and now the calculator is thinking. And notice that the regression is in the form a plus b ln x, and this is the value of a and the value of b. But look at the correlation coefficients. The r squared coefficient is 0.849. This is not a very good correlation at all. And if we want to see the graph, we can do that easily. Let's cursor down to y2, and we'd like to enter this graph automatically, or the information about the graph automatically. So vars, item number 5, cursor to the right twice for equations, and then enter. And here we have the equation and now the graph. Now the linear equation is already on board, but notice that the natural log graph is coming up, and it's kind of in the shape that, or the behavior of the graph, the appearance of it is as we would expect it to be. And it certainly does not match our information very well. Well, let's perform another regression. We would probably have thought at the beginning that the best regression would be an exponential regression. So let's go to the right and calculate an exponential regression. Here we are, enter, and then enter again. Now look at those correlation coefficients. They're very close to 1. And that tells us then that we're going to have a fairly good match. Look particularly at the r squared. It's 0.998 and 0.9987 and so on. And I want to call your attention to this because we're going to perform one more regression in just a little bit. This is going to be the best regression for our purposes because we are in a chapter of exponential and logarithmic functions. But there is another regression that works particularly well on this set of data as well. Well, let's go to the graph. We are going to press y equals, and then we'd like to cursor down to y3, and then we want vars, item number 5, right, oops, vars, item number 5, I didn't get the 5 pressed, and then right, and enter, and there we have our third equation and the graph. Now, you see, it appears to be just going right through those data points, and that's what we want to see. Every now and then we'd get one maybe off of that line, but we'd like to see it as close as possible to the information. All right, so our exponential graph works best. Let's perform one more regression right quick. We'll go stat, and then right, and then down to the quadratic regression, and I'll press enter, enter. And what I want you to notice is this high r squared coefficient, 0.9989. Now, the one for the exponential regression was 0.9987, so this is a little bit better even to describe our data with an equation. And notice the equation is in the general form of the quadratic, and here's the value of a, b, and c. Okay, we can see the graph then by going y equals, and then we'll cursor down. I tell you what, we don't need this this linear graph. Let's clear this, and I think I'd like to also clear this one, and in place of y1 I'm going to enter the one that we just performed the regression on, and to do that I will press vars, and I want statistics number 5 to the right 2 places and enter. And here we go. Let's look at this graph. Now we're overlaying this graph with the other graph that fits well with this. And they're just about, you can just see kind of a double line in some places. It almost looks like it's just a little thicker in places. You see it's coming up here. And so both of these match the information extremely well. We would probably, depending upon what we wanted to calculate about this data outside of this region. You see, we might want to calculate things about the correlation between x and y that's outside of this data range, something for future information, something that's out here on the graph, you see. And the graphs tend to part up here in the coordinate plane. In fact, let's have a look at how they do begin to digress from one another. I will press window, and I'd like to go out to the right a little bit, so I'll change the x max to, instead of 4.64, I'll go out to about 7. And then for the y max, I'll go out to about 13. Well, let's make it 14, and then look at the graphs. And I think this is enough to see that they are going to begin to separate, but we'll know in a second. Yeah, they're just starting to separate here at the very top of our viewing window, and if we changed our window and went up quite a bit more, we could see that they change even more the further we go up. So it depends a little bit on what we're after with this set of data as to which one of these models we might use. Crash testing contributes information useful in improving safety features in automobiles. Engineers often alter the design of vehicles according to the results of crash testing. Here's an example of that situation. In order to protect the occupants of automobiles in accidents, the automobiles are designed with crumple zones. The crumple zones allow the occupants to move short distances when the automobiles come to abrupt stops. The force experienced in stopping abruptly is measured in G's. 1 G is equal to the force of gravity. Now, the greater the distance moved, the fewer G's the crash victims experience. Most people will black out under a force of 5 G's if it is applied for 10 seconds or more. Now, 5 G's simply means 5 times the force of gravity. For very short durations, humans have withstood as much as 40 G's. In crash tests with vehicles moving at 55 miles per hour, analysts measured the numbers Y of G's that were undergone during deceleration by crash dummies that were permitted, using crumple zones and passive resistance systems, to move distances of X meters during impact. Here's a table showing the result of experiments in that area. Now notice the distance is x. X is a distance in meters, and y is the force measured in G's. Now let's make a scatter plot of the data. First we'll enter the information, and we do that by pressing Stat and then number 1 or Enter because we want to edit. And I've already entered the information, and this item, for example, means that a distance of 0.8 meters corresponds with a force of 40 G's. Okay, now let's have a look at the scatter plot. Press second and then stat plot, that's y equals. And we just want to turn this on, so I'll press enter and then enter again. And now it's on. And to make the appropriate window settings, press zoom. And then we want item number 9. I'll cursor down to it so we can see it. Zoom stat, this is an automatic window setting for statistics. And here we go. So here's our scatter plot, and we can press trace and verify that these are the values that we entered, the values that are on the table, and such things as that. Okay, suppose we want information that's not found in the table. For example, suppose we'd like to know the distance associated with a force that is not to exceed 30 G's. Now, right here on the scatter plot, I have a distance of 1 meter associated with 32 G's. So a distance associated with 30 G's would presumably be to the right or more distant, you see, a greater distance than 1 for our experiment. Well, in order to find that, we can make a mathematical model. Now, let's use a regression, an internal regression on this and see what it gives us in terms of information. We'll press Stat. And then we want to calculate, so I'll cursor over to calculate, and we'll choose one of the models. Let's use the natural log model. It's item number 9, the LN regression. We could choose a couple of others logically, I suppose, but let's just use this one for our discussion purposes. All right, so here we have the regression, and I'd call your attention to the correlation coefficients. Now, I mentioned earlier that correlation coefficients are very accurate as they approach 1, and it turns out that they are very accurate as they approach either 1 or -1. And here we have -0.977, and actually that is not particularly accurate. Let's see why. This emulates the data but not extremely well. Now to view the graph with the scatter plot, we're going to need to enter the equation by pressing VARS and then number 5 for statistics. And then we want an equation, so we cursor over to that, press enter, and here's the equation. And now graph. You see how the graph is just not going through the data points? And in fact, when we press trace, I'll cursor over to the right. Now I'm on the scatter plot, and I'm going to jump down onto the curve, and I'll cursor over where y is around 30, and it's in this neighborhood, you see, that we would like to be. But notice the x value is 0.89, and we know that that distance that an occupant travels needs to be greater than 1, so this is just clearly inaccurate. Now a much more accurate equation is this one. I'll cursor down and just enter it for you, but it is this. It is -3. Now this doesn't come from a regression model. This actually comes from an engineer that has worked on this kind of problem. So it's -3 plus 11.88 ln x, close parenthesis, plus a fraction, and the fraction is 36.94 divided by x. And now take a look at how accurate this graph is. And notice it goes through the data points almost exactly. And this then would be a much better mathematical model to use for us to decide about a distance. And let's do that. Let's trace, and then I'll jump onto that, that equation. Here's y2, and we're on it here, and I'm going to cursor over. I'll just leave the right arrow button depressed, and I'm looking at the y's blinking at me, and I'm looking for a y that corresponds with 30, and oh, I don't see it here, and I'm just about off the graph. Well, let me change my window settings, and I'll change the x max to 2, and back to the graph, and the graphs will have to be redrawn. Actually, in redrawing the graphs, we're going to see that how much the graphs begin to digress from one another in this part of the coordinate system. You see, they really start to part right in here, and this is where we want our information. So at any rate, graphing or tracing, we want to trace all the way over. Let's see, oh, I have a y of, I'm all the way over to 28. Here we go. 29.94. Oh, that's pretty good. And the distance associated with that is 1.2. So the distance traveled by an occupant, we would like for the engineers to design those crumple zones so that the distance is 1.2. Now, you know, if those engineers are designing crumple zones for my car, I'd like them to use the most accurate mathematical model they can possibly generate. And that is the importance of learning how to generate mathematical models. And more generally, that's the importance of mathematics in the overall process.